Yes.
It's an actual plot of picture.
Yes.
Oh.
It's not in the paragraph, just telling me what patterns you see, or what the trends are for acid strength. That's what I'm looking for. All right, talking about acid strength. Was there a correlation between the positive potential, on the hydrogen? That would have been the maximum positive potential, whatever, potential that is, either the minimum or the maximum, since looking at the magnitude of the number. Was there a pretty good correlation with the delta plus on hydrogen and acid strength? Yeah, the answer is yeah. There was a pretty good correlation. There's a graph there. Not every point lined up on the line, but the correlation you could see. And so, it wasn't a perfect correlation, though. And so there must be other factors involved in acid strength. And so let's take a look at the factors affecting acid strength. Acid strength is going to depend on, first, the bond energy. The bond energy, for the HB bond, B is just your generic base. It's base because, when the acid loses an H+, what we're left with is a conjugate base. This is how one acid differs from another. It depends on what the anion is of the conjugate base. And so bond energy is important here. In fact, if we were to make a plot of potential versus this delta plus versus a pKa. For the series HF, HF has a very big delta plus on it. But HF, is it a strong acid? No, HF is a weak acid. And so HF has a big delta plus, but it's a weak acid, so it has a high pKa. So HF is something like this. Here. HCl has a big delta plus, but it's a strong acid. So strong acids have low pKa. So HCl is something like this. And then HBr has a smaller delta plus. And then HI has the smallest delta plus. And so when we look at this trend looks quite a bit different. There is an outlier here, and the outlier would be HF. And so let's just look at this series, HCl, HBr, and HI. And look at this series. The pattern looks like this. We fit it with a trend line. And so as we increase delta plus, the acid gets weaker. Is that what you observed yesterday? As delta plus increases, the acid gets weaker. No, that's not what you observed yesterday. What did you observe yesterday? This is what I mean by paragraph. A simple paragraph or a simple statement might be as delta plus on the hydrogen increases, the acid gets stronger. So let's take a look here. And so this trend is completely backwards from what we just observed. Since this is completely opposite of what we just saw, does that mean there's really no trend? It's really difficult to predict. And no, that's not what it means. What it means is, okay, there must be other factors that impact this. This is why I say this is backwards from what I thought. When you're looking at the delta plus on hydrogen, you would think HF is the strongest acid, followed by HCl, HBr, HI. But the reverse is the case because the acid strength, the number one factor in dictating acid strength is bond energy. How easy is it to pluck off that hydrogen? Yes, you will need some polarity, because if you don't have any polarity, the base won't be attracted to it. And so there's got to be some delta plus, a little bit of delta plus to attract the base. Another base, not this base, but another base comes along and plucks off that hydrogen. And so HI is going to be the strongest acid. The strongest acids are going to have the lowest pKa because of the bond energy, right? And so why did the correlation work then? Why did your correlation work? Actually, I want to go here. Save. So I copied. I think this is Utimas. Who is this? Your graph? So we see it as the delta plus gets smaller and smaller, the acid gets weaker and weaker, and it's a pretty good correlation here. The reason it's a pretty good correlation is because the bond energies are all the same. These are all carboxylic acids. They all have the OH bond to break. And so when we normalize this so that there's no difference in the bond energy, then the next most important factor is polarity. And so, well, how do we know which one was most important? Was it bond energy or polarity? Because they say opposite things. Polarity says HF is the strongest. Bond energy says HI is strongest. Well, which one won in this particular case? Well, this is experimental data, and therefore bond energy is the most important factor. So we see bond energy is the first thing we look at. Now, if all the bonds are the same, like the carboxylic acid, then we consider polarity. And when we consider polarity, yeah, the bond energy is the same. It looks like it. The most polar and the most acidic. This one's the most polar. It's the most acidic. It has the lowest pKa. The least polar. That's the least polar. The least polar should be the least acidic. The least polar is benzoic acid, but is it the least acidic? No. So we're going to ignore, this is what I mean by outline, we're going to ignore this because there's got to be some other factor that is causing benzoic acid to be weaker than expected. Because based on the polarity, benzoic acid should be where? Well, based on polarity, benzoic acid, if we follow the trend line, benzoic acid should be here. pKa, a pretty high pKa, meaning a weak acid. But benzoic acid is unusually strong. And so we have to figure out, well, there must be more factors influencing the acidity than just these two, right? Because the bond strength is the same, essentially, close enough, but there's something else. But other than that, it seemed like these, all fit, although it's not a great correlation. It's not perfect correlation. And so there's got to be other influences on acid strength, which there are. And so benzoic acid is unusually strong. What makes it unusually strong? So going to the next thing. from polarity. Increasing polarity, decreasing bond energy, stronger the acid. Increasing polarity, the stronger the acid, ignoring everything else. And the third factor is going to be the stability of the products. The stability of the products, okay, when the proton leaves, we're left with the conjugate base. And so how stable is the conjugate base? So we'll just say conjugate base. Stability. So if we're looking at a stable base, then we want something that's unreactive. Something that's stable is unreactive. And so what makes a base more reactive or less reactive? So let's take a look at that. Basically, we look at something called charge density. So let's compare two bases. Well, when we look at charge density, we look at two major factors influencing charge density. One factor is the inductive effect. And the other factor is resonance delocalization. And so let's look at how these factors influence basicity. If we look at charge density, let's compare two bases. Hydroxide versus oxide. Hydroxide versus oxide. Normally when you do Lewis structures, you add up the formal charges, you get the net charge. So we put this in square brackets and do this. But I'm just going to eliminate that. Just write it like this. Normally with oxide, we just don't circle it. With hydroxide, we typically circle it. So this is how it normally looks, but it's not consistent. Which one's a better base? Hydroxide or oxide? And why? Well, what do bases want to do? Bases want to attack the acidic hydrogen. And so when we're thinking about acidic hydrogen, if you're going to attack the acidic hydrogen, one, the bond shouldn't be too strong, otherwise it's going to be too hard to break. And two, the base has to grip onto something on the hydrogen. What is the base going to grip on? The base is going to grip on, well, all chemical reactions are electrical in nature. And so what's going to attract a base to an acid is that the hydrogen has a delta plus charge. It's polarity. And so both of these are going to be attracted to an H+. Now, which one will have a stronger interaction or attraction to an H+? The oxide or the hydroxide? Yeah, and then polarity is tricky because polarity. When we're talking about polarity, we're looking at dipoles usually, but we could also have monopoles. Both of these are highly polar. For example, oxide is highly polar. This is just a monopole. This is negative charge. That's it. And so it's one pole. This is also a negatively charged species here. You're right, there's going to be some kind of dipole moment in there, but it's not that what we're looking at. What we're looking at is something like an active site. If you look at an active site, what makes hydroxide basic? It's not the hydrogen, it's the oxygen, because the oxygen is what's going to attack the acid. The acid is H+. So which one's going to be more effective at attacking H+? Well, the one that's going to be more strongly attracted to H+. And which one of these two is more strongly attracted to H+? Oxide. Why oxide?
Like you said, it's only the one pole.
Well, this is kind of a monopole also, because the whole thing is negatively charged. There's no, you know, you could write a delta plus here and delta minus, but that would just enhance the charge. This is a full negative charge here. It's an ion. Ions are monopoles. Well, it has to do with Coulomb's law. Coulomb's law is something that they discuss in physics, but Coulomb's law was also introduced in chapter 1 of our book, and Coulomb's law says that the attraction between charged species is going to depend on the magnitude of the charge and the distance. Well, we don't look at magnitude and distance because we aren't sitting there measuring distances. Instead, we think in terms of charge density. Charge density is, you know, charge per unit volume. And so the higher the charge per unit volume, the higher the charge density. Well, the unit volume should be about the same because they're both oxygen atoms. What's going to differ is the amount of charge. You know, this oxygen contains -2 charge. This oxygen contains -1 charge. And so what we say is that oxide has a higher negative charge density than hydroxide. Well, what is acid? Acid is H+, you know, plus positive charge. And so looking at it from purely like a Coulomb's type attraction, a -2 is going to have twice the force of attraction than a -1. And so the interactions double that. In other words, you know, this is just simple approximation. Sometimes we do simple approximations like that. You know, it's like in the same thing in quantum mechanics. Sometimes you do simple approximations. And so one of the simple approximations is, well, this is going to have twice the reactivity because it's got twice the charge, you know, than this. But that's a very, you know, that's a simplification. What's that? It's got twice, no, -1, -2, it's twice the charge. You know. If you double the charge in Coulomb's law, you double the force. And so oxide is expected to be a better or stronger base than hydroxide. In fact, that's what we see. You look at the base chart. You see hydroxide down there at the bottom right? What's stronger than hydroxide? Oxide. Oxide's stronger. Well, versus, go with sulfide. Sulfide is a -2 ion, just like oxide. And since they're both -2, are they going to be equal in strength? No, because we look at the magnitude charge and the concentration of that charge via the volume. And so when we compare these two, oxide's smaller, and that has a -2 charge contained in this volume. Sulfide is bigger and has a -2 charge. And so what we can do is we can say that this is concentrated, this is more dilute. So what's going to be more reactive, a concentrated or dilute? Concentrated. And so we don't say concentrated, we just say this has a higher charge density, even though the magnitude of the charge is the same. They're both -2, right? The charge density is quite a bit different. This has a charge density of that's much higher than the other. Therefore, oxide should be much more reactive than sulfide. And so oxide is a bit better base. Oxide is a better base than sulfide. Let's compare hydroxide to to sulfide. That's a trickier comparison because here, on the one hand, the charge is double, but what about the size? Does the size double compared to oxide or hydroxide? And so over here with hydroxide, we got a -1 charge here, and sulfide is a -2 charge. Which one do you think is going to be a better base? Sulfide or hydroxide? That might be too tricky to answer because, how do you weigh these things and what are the size differences? But what would your guess be? Hydroxide or sulfide? Hydroxide because it's smaller, or sulfide because it has a higher charge? You're thinking metathesis reaction, so no, we don't want to think in terms. We're just doing Bronsted acid base. So this is for Bronsted. Lewis are much more trickier. So Bronsted acid strength. So on the one hand, hydroxide should be a better base because oxygen's smaller. On the other hand, sulfide should be a better base because it's got twice the negative charge. And so which one of these do you think wins? Is it sulfide or is it hydroxide? Well, if you look at the chart, what does the chart say? Which one's a better base? Hydroxide or sulfide? The chart says hydroxide's a better base. You see that? But unfortunately, this chart is wrong. This chart was published in 1998, but the data was decades earlier, and they've never updated it. Sulfide is a more powerful base than hydroxide. I corrected it here. It should be 10 to the minus 19, which places it over here. So hydroxide, sulfide, and then oxide. So the -2 charge common. Amid's tricky because you think amide, why is the amide there? That's the strongest. And so there are other factors influencing this in addition to charge. All right, so it would go hydroxide, sulfide, and then oxide in terms of strength. Yeah. Okay, so that's dealing with charge density. Now, things that impact the charge density would be something like the inductive effect. And so let's talk about the inductive effect now. Here's an example here. Let's compare these two species. We're going to compare hydroxide versus this. Do you know what that is? Hypochlorite. This is a hypochlorite. So let's compare hydroxide with hypochlorite. Well, we got oxygen with negative charge, oxygen with negative charge. Both oxygens with negative charge, so the charge density should be the same, right? And therefore, if they're the same, then they're going to have the same basicity, the same strength. But are they really the same? No, they aren't the same. Because we know something. You know, hydrogen versus oxygen, which one wins? There. Oxygen. And so when we look at this, this is going to be an sp3 sigma bond. And when we look at the two electrons in that bond, they're going to be polarized towards oxygen. And so the electron density in the sp3 sigma is polarized towards oxygen. Whereas over here, if we look at the sp3 sigma, chlorine and oxygen are more comparable in terms of electronegativity. And so if there's a tug of war, it's not going to be lopsided. It's going to be more even. And so here is how that sp3 sigma would be more like. And so, in other words, when we compare and look at the differences, in this case, compared to hydroxide, chlorine is pulling more of the charge density or the electron cloud away from oxygen. As chlorine pulls the charge density away from oxygen relative to hydroxide, what's that going to do to the negative charge density on oxygen? It's going to decrease it. Over here, we're going to have a higher negative charge density. And so in other words, chlorine is a more electron withdrawing group. Electron withdrawing species sucks or pulls electron density away compared to hydrogen. Hydrogen is more of an electron pusher because it's not as hard to take the electron density away from that. And so, in other words, which one is a stronger base? Chloride or hypochlorite? Hypochlorite is a stronger base. Is it? Well, what makes a strong base? A strong base has more negative charge density on the active atom. The active atom in this case would be the oxygen. And so which one has a greater negative charge density on the oxygen? Hydroxide does. And so it turns out that hydroxide is a strong base, hypochlorite is a weak base. Although it's moderate, it's not totally weak. It's moderate in strength. But still it's considered weak because it's not strong. And so weak base, strong base. And it's because of, this is called, when we look at it, it looks like the negative charge density the same, right? What's happening is called the inductive effect. The inductive effect is this electron sucking or electron withdrawing effect due to this, having this electronegative species on there. The inductive effect. All right, let's continue on. Versus hypoiodide. Hypoiodide compared to hypochlorite. Which one do you think is a better base? Hypochlorite or hypoiodide? Both are weak. But which one should be a better base and why? Hypoiodide should be a better base, right? Because iodine is a lot less electronegative. So chlorine, compared to chlorine, it's going to lose more electron density to oxygen. And that means we're going to build up more negative charge density on oxygen, which is going to make it more basic. And so out of these, it would go, hypochlorite's the weakest, followed by hypoiodide, followed by hydroxide. Hydroxide being the strongest. And so how would you explain this? A lot of people say, hypochlorite's weaker because it has a higher electronegativity. No, electronegativity, you don't want to explain bases in terms of electronegativity. If you do use electronegativity, you have to talk in terms of how that impacts the active atom. Because bases, are they electronegative? Do bases want electrons? Bases don't want electrons. Bases are what we call electropositive, not electronegative. And so somebody who says, sulfide versus oxide. Oxide should be a stronger base because it's more electronegative. It makes no sense. You know? As far as base goes, in a way it makes sense because more electronegative pulls in the electrons tighter, making it smaller. It's because it's smaller, this higher charge density makes it more electropositive, makes it a better base. Unfortunately, Petrucci uses that in some of the homework. He says that this is more basic because this is more electronegative. In fact, he uses it for oxide versus sulfide, but you shouldn't use that. Okay, and the answer. It's not Petrucci, it's whoever did the answers in the solutions guide. It was seven different people. Unfortunately, that answer wasn't right. All right, that's the inductive effect, and we'll see that. And we always look for that happening. And the next one is a bit more dramatic. Look at this. What's more basic? This is called ethoxide. Ethoxide versus hypochlorite. Ethoxide versus hypochlorite. Which one is a better base, ethoxide or hypochlorite? Ethoxide? That's true. Ethoxide is a better base. That's because what's attached to oxygen is quite a bit different. You know, this is an electron withdrawing group. It's sucking electron density away. In fact, do you know what the oxidation state of chlorine is here in hypochlorite? Normally the oxidation state of chlorine in compounds is -1, but not in this case. What's the oxidation state of chlorine in this particular compound? Well, let's answer this first. What's the oxidation state of oxygen? I should have done -2. -2 plus what gives us -1? +1. So the oxidation state is +1 here. What we call electron, withdrawing group. Electron density is being sucked towards the chlorine. Right? This is why I wanted you to write all the numbers. Some people ask me, do you need to write all the numbers down, the oxidation? Yeah, you want to, because then you'll get a better picture of what's happening. Once you process all that information. But hard part is processing all that information. Whereas, let's look at the oxidation. What's the oxidation state of this carbon here? -2? 2, 4, 5, close. Not -2. -2 is wrong. It's -1. See? So the oxidation state of this is -1. And so this is totally different. What's the oxidation state of carbon over here? -3. And so when we look at this, this is what we call an ethyl group, an ethyl group attached to this oxide. When we look at this, or this oxygen, when we look at this group, hydrocarbon groups, are they kind of sucking electron density away? We think of a hydrocarbon as being electron poor, and so it sucks electron density away? Or would you think of a hydrocarbon group, like this alpha group, as being electron rich? and kind of pushing electron density. Do you see this? When you look at this, I see this, right? When you look at this, do you see this? You know, this is a -1 charged carbon. It's going to be pushing electron density. Well, this is negative. This is true negative. This is a oxidation state. But anyway, when we think about this group here, this is kind of electron rich, right? This electron rich, it's going to, in fact, hydrocarbons are electron rich because they're good fuels. You can burn them, right? They're good reducers, react with oxidizers. And so looking at something like ethoxide here, you know, what do you see? I see this is electron rich. In fact, ethoxide is going to be comparable to hydroxide in terms of basicity. Now, there are different ways we can do it. We can look at electronegativities. Carbon has electronegativity 2.5, hydrogen has electronegativity 2.1. So it should be comparable, right? But not only that, ethoxide has this -1 formal charge, or not formal charge, oxidation state on carbon. And so ethoxide's a powerful base, but you know, that's not one of the ones on the list up there, but it's one of these ones that are known, well known.
I'm still trying to process the hypochlorite one with the +1 oxidation state. What is that? Does that tell you that, do you take that into consideration for the state, if it's stable or not?
No.
No? Or just...
We're just taking into consideration that, you know, it's going to suck electron density away from oxygen. So we're just looking at the numbers and trying to figure them out. Whereas, you know, this one is a -1. And so we look at different things. We look at electronegativity. You know, chlorine's 3.0, carbon's 2.5. Chlorine's more electronegative, it pulls electron density. And so other ways of representing this are like this. This is the inductive, it's sucking electron density away from oxygen, more so than in hydrogen. Over here, there's no inductive effect, it's not pulling. And so this group is not withdrawing electron density away from the base atom. It's more like feeding it electron density. And so we call it electron pusher group versus electron. This is why I wanted you to write all the oxidation numbers so you could see, you know, all the acids that we dealt with were carboxylic acids. The only thing that was different was what was bonded to the carboxylic acid. What's bonded to the carboxylic acid is going to influence electrical properties of the carboxylate group, depending on if it's sucking electron density away or giving it electron density. And so, yes, I need you to write all the oxidation states so that you can more properly analyze it, because these hydrogens aren't really going to do much. And so there's no inductive effect here. No inductive effect. Well, that's ethoxide. Actually, let me do a little less writing. We call this a methyl group here, like methane. It's just missing a hydrogen here. And so methyl group, like methane, you know, methane is electron rich or electron poor, methane? Electron rich. The methyl group is also electron rich, you know. When I'm thinking about the base strengths, let's compare methoxide with one of those. When we look at this, methoxide, what do you expect? Strong base or weak base? Strong base. How could you tell? Well, one, you might just, oh, you could see it. Do you see it according to electronegativities? Can you see it? You just, oh, well, yeah, this is a 2.5, this is 3.0, this is going to be a strong base. Or do you see it according to, sp3 sigma, and the polarizability of the electron cloud? Or do you see it according to oxidation state? What's the oxidation state of carbon here? Oxidation 2, 4, 6, negative 2 is right. You see it as being electron rich according to the oxidation state. And so what you're doing is you're trying to come up with the correlations. And so what I want you to do with that lab is to take a look. Do you see any correlations there? How do you perceive these numbers? Are they of any practical use? Well, formal charges aren't, but some of this other stuff is. This is a powerful base. Methoxide, ethoxide, both of these are very strong bases. Now, what if I did this? What if I went from methoxide to it depends. What if I went from methoxide to this? Trichloromethoxide. Yeah, trichloromethoxide and methoxide, are they going to be comparable in base strength? Not at all. I mean, can you see what's happening with the electron cloud here? That's the inductive effect. If you can see what's happening, so the way this is visualized in Petrucci is he does this. Electron cloud is being sucked away by these chlorines, right? So it's electron cloud. That means this carbon's being deprived of its electron density, which makes it more positive, which is going to suck electron density away from that oxygen. And so something like methoxide is a powerful base, but trichloromethoxide is a weak base. This is very weak. Do you guys see that? That's, there are different ways of seeing this, and it depends on how the numbers work out. For example, what's the oxidation state on carbon here? Oh, this is better. What's the oxidation state of carbon here? +4. And so these two groups are on the opposite ends of the spectrum. This group is, literally this group is more of an electron pusher group. This was what, 2, 4, 6 is -2. It's got an electron rich, electron pusher group. Whereas trichloromethane is at the opposite. This is going to be sucking electron density away from this. As it sucks electron density away from the oxygen, it's going to make the oxygen less negative, which makes it a lot less reactive. Over here, the oxygen is much more negative, making it much more reactive to this charge. Well, something that looks similar to ethoxide is acetate. And so let's take a look at acetate. Acetate has a CH3 or methyl group here at the end, but it has the carboxyl group here. And since this is the anion, we call it a carboxylate group here. And so when we look at this, the C, negative charge here, versus this, and both of them have this methyl group attached here, are they going to be similar in terms of basicity? Ethoxide's a powerful base. Is acetate a powerful base? No, acetate is not a powerful base. In fact, acetate's a weak base. So why is that? Well, it's because of this. You know, this might be a methyl, but when we look at this, in organic chemistry, this is called a methylene group, or this whole thing would be called a ethyl group. But over here, when we look at this carbon's a lot different than this carbon. You know, this carbon, you know, well, you might say they're both carbons. Carbon has electronegativity of 2.5. And so both of those have electronegativity of 2.5, so is there really any difference? No, there is a huge difference. This is why I gave you this problem. This problem was in, which one's a better oxidizer? F or F plus? Well, somebody might say, well, they're both fluorine, therefore they're both the strongest oxidizer, right? And they're equal, they're the top. No, you know, this is over the top of that chart. Because this is going to be a much more powerful oxidizer than F2. And so these two carbons aren't equivalent. For example, fluorine has an electronegativity of 4.0. And so does that mean this has a 4.0 and this has a 4.0? No, this is above 4.0. This has electronegativity higher than 4.0. I don't know what it is, but it's got to be higher. And so the oxidation state on the carbon, this is why I want you to write the oxidation states, because then, you know, it's clear that these don't behave the same, these two carbons. If you just memorize this according to electronegativities, it doesn't tell you any difference unless you do all these arrows and other stuff. But it is pretty obvious, having another oxygen rather than two hydrogens. Oxygen is going to be an electron withdrawing group, but you know, we could see this. There's two ways you could see this. One, just go ahead and do the oxidation state. What's the oxidation state of this carbon here? What is it? Plus 3. Plus 3 is correct. And you can see that these two these two carbons are totally different. One's plus 3, the other's minus 1. One's electron rich, the other's electron poor. And so having this electron poor carbon here, what's that going to do to the charge density here? It's going to suck it away, right? Even though normally we go 2.1, 3.5, or no, 2.5, 3.5. 2.5, 3.5, oxygen is going to be sucking electron density away. But no, in this case, carbon's going to have a big pull because of the plus 3 charge. And so, you know, there are different ways we can represent it. And one way, as Petrucci does, is this sucks electron density away from the carbon, which in turn is going to force the carbon to suck electron density away out of the red. But we could already see that, you know, this is the reason why we got a plus 3 here, because of this oxygen. And so it turns out acetate is a weak base, ethoxide, strong base. But, you know, this inductive effect is not the most important. If it was just an inductive effect, it wouldn't accurately describe why acetate is such a weak base. In this case, it turns out acetate is a weak base because of something called resonance delocalization. When I come up with acetate, I generate two resonance forms for this. One with the negative charge on this oxygen, and the other with the negative charge on this oxygen here. What's more accurate is not either of these. What's more accurate is the resonance hybrid. The resonance hybrid is going to look like this, where both bonds are equivalent. There are two lone pairs fixed on each, and then one lone pair that's delocalized or floating between the two. Here. The bond order is 1.5. It's 1.5 bond. And the formal charge, well, we have -1 shared between two oxygens. So -1 shared between two will be -1/2. It'll be -1/2. And so what happens is the charge density gets cut in half, you know, it's a simplification, you know, but essentially that's what happened. Whereas the inductive effect isn't going to do that. And here, the carbon's still a +3 oxidation state. And so we can have, you know, not only do we have this, but we can have electron density being pulled towards carbon, further reducing the negative charge density on the oxygens. And so this turns out to be a very weak base, you know, resonance delocalization. What if we do something like this? What if we make I'll just do the hybrid. What if I do something like that? I do trichloroacetate. Which one is a better base? Trichloroacetate or acetate? Well, here, you know, it looks the same because I got -1/2, I got a +3 oxidation state on that carbon. And so are they the same? No, they're different because we look at this structure as a whole, and we look at how the electron cloud is distributed in the whole structure. And so what do you see is different? Can you see these two are totally different? And what's totally different is what's bonded to that carbon. Over here, this is methyl. Over here, this is a trichloromethyl. Totally different, right? Trichloromethyl is going to be sucking electron density away, versus methyl is going to be pushing electron density. We can see that in the oxidation states here. Oxidation state of this carbon is 2, 4, 6, 7. What's the oxidation state of this carbon? This is a -3. What's the oxidation state of this carbon here? +3. Do you see now? Yeah, well, you probably saw it earlier, but this is going to be much more electron withdrawing, you know, than this. And so, well, if this is much more electron withdrawing, it's going to suck negative charge density off the oxygens, making it less reactive. The more negative charge density on the oxygen, the more reactive. So this is much more electron rich, so it can push electron density this way. All the carboxylic acids are the same. They're going to have the carboxylates, they're COO. Carboxylic acids are going to be COOH. We have the conjugate relationship too. You know, the stronger the acid, the weaker its conjugate base. And so here, trichloroacetic acid is a stronger acid, and therefore its conjugate base is weaker. This is a weaker base. But that's not how we'd argue. We'd argue based on, you know, electron clouds and this kind of stuff. You know, because sometimes I ask, you know, what's a stronger base and why? And so somebody might say, well, this is a stronger base because its conjugate acid is weaker, but that doesn't really explain structurally why. You know, I don't really consider that a good answer. So it could be because the it could be that benzoic acid is a stronger acid than expected because its conjugate base is more stable than expected. And so let's take a look at benzoic acid right now. But before that, let's look at benzene. Benzene is a pretty interesting compound. This is one of the resonance forms for benzene. And altogether there are 2 resonance forms. So there's the 3 double bonds here or the 3 double bonds in the next position over. When we look at benzene, what's the hybridization on carbon on each of these? It's sp2 hybridized. And so let's go ahead and draw a valence bond picture of that. All right, so here's my drawing of all the sp2 orbitals. And so we're going to see sp2 sigma bonds here between all the carbons. So sp2 sigma bonds. And then we're going to have sp2 sigma bonds for the hydrogens here. So H. And so this is the benzene ring here. This is the sp2 network. These are hydrogen S. This is sp2 hybridized, then there's going to be an unhybridized p orbital. And, those are going to be coming out the board. So this is flat as a plane. Then I'm going to have double bond. I'm going to have a double bond between these 2 carbons, so I need a pi bond here. Okay. I have a double bond between these 2 carbons, so I need a pi bond here. And between these 2 carbons. 3 pi bonds. 1, 2, 3. But if you look at the orientation of all the p orbitals, you know, what's preventing this from overlapping this one? Nothing. They're all oriented perpendicular to the sheet. And so what happens is this. What we see is this is a localized pi bond here, a localized pi bond, and a localized pi bond. What we see is a delocalization of the pi bonding network. In fact, it overlaps here, 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 here. In fact, all the p orbitals overlap because they're all properly oriented. And so what this does is it delocalizes the electron. All of a sudden there was a wall here, but there's no wall there really. There is no wall here. If there's no wall here, then the water can flow. In other words, the electron cloud can flow. Well, if electron cloud flows, then that means the pi electrons are not localized. The pi electrons are completely delocalized across the ring. Well, what that's going to result in, it's going to result in a resonance hybrid. The resonance hybrid is going to look similar to this, because the resonance hybrid looks like this. You know, the pi electrons are delocalized over all the carbons. And so I'll just draw a circle like that, indicating that. What's the bond order? What's the carbon-carbon bond order? So this is the hybrid. In fact, the MO looks like this. What is the bond order? The bond order should be 1.5. It's a 1.5 bond. But it turns out that these are greater than 1.5 bonds. So that is, these are unusually strong bonds. Unusually strong and stable. You know, it's still reactive. Benzene burns stuff. But it's stronger than what you would expect. And the reason it's stronger than what you expect is because of this. This is called a conjugated network, where you have single, double. Whenever you have this situation where you go single, double, then all the carbons are sp2 hybridized. If they're sp2 hybridized, then that means we can delocalize the pi electrons over a large area of the molecule. And so this type of compound, where we have a delocalized pi bonding network, is called an aromatic. Aromatics are stable in the sense of not stable. They're still reactive. You can react them, but they're stable compared to not having a delocalized pi bonding network. And so you can read more about benzene. And there are different series. They don't all have to be rings. You could have aromatic chains, aromatic rings, etc. This is a class of organic compounds. So, you know. Well, you know, is benzene going to be an electron withdrawing group, or is it going to be an electron pushing group? You know, that's what we want to figure out. You know, how is benzene going to impact it? Well, let's take a look at acid strength. And benzoic acid. I'll just draw one resonance form of this. Really, the hybrid's probably the best. Here. And so, is this benzene going to? Oops, this is. I'm sorry. This is not a base. This is acid. Benzoic acid. And so here's my carboxylic group, or carboxyl group, COOH, right? And so what do I have bonded to the COOH? Well, I have a benzene ring bonded to it. Is a benzene ring going to be an electron pusher or electron withdrawer? And then you think, well, you know, the pattern I saw is hydrocarbons. Hydrocarbons are good fuels. They burn easily. So hydrocarbons are electron rich, right? Hydrocarbons being electron rich, it should be electron pusher. And so if this are pushing electron density towards this, it would make it less acidic or more acidic? So if this is pushing electron density towards the carboxyl group, does this make it more positive or more negative? The hydrogen. So as negative charge density gets pushed here, the result is it becomes more positive. Actually, as negative charge density gets pushed over here, it becomes more negative. Well, does that make sense? Well, let's take a look at the oxidation states. When we look at the oxidation states, we see this. What's the oxidation state of carbon here? 0. What's the oxidation state of carbon here? -1. This one? Saying -1, -1, -1, -1. So if you were to think about this, you'd probably think this is more electron rich or more electron poor? More electron rich. This electron rich is pushing electron density towards this, making this less acidic. Right. And so is there another reason why benzoic acid, it would make sense if it were electron poor, because if it's electron poor, make that delta, you know. But then again, if we're electron poor, if this were electron poor, it'd suck electron density from here and make this hydrogen more positive. But when we look at how positive that hydrogen, it's not very positive. Look at the potential here, the energy, pretty low. Saying that hydrogen is not that positive, so it's not that polar. And so what's happening here? Well, it's not due to bond strength and doesn't appear to be due to polarity, right? It's got to be due to something else. What's it due to? Maybe it's due to the stability of the, what? Conjugate base. And so let's take a look at the stability of the conjugate base. The stability of the conjugate base is going to look like this. This is called the benzoate ion. So the benzoate ion, what we see is we see resonance delocalization. Right? The resonance delocalization will be between these two oxygens here. In fact, the formal charge on each oxygen will be minus ½ But what's going on? And so when we're thinking about resonance forms, the more resonance forms we can draw, the more the electron density is spread out over the structure. And so one of the rules you learn in organic chemistry is that the more resonance forms, the more stable, less basic. Or the more resonance forms, the more stable. When you're comparing base strengths, be less basic.
If you have more resonance for acids, would it make them more acidic?
That, for acids, is more tricky. You know, for acids, not necessarily. You know, for bases, because you're delocalizing the charge, but for acids, a little bit different. And so let's take a look at an example that's a little more clear. This one's not hard. This one's kind of hard to see, but it looks like the charge can be delocalized over these two oxygens, just like, you know, acetic acid, just like any of these others. But it turns out that some of the charge can be delocalized in the ring. Now, how can some of the charge be delocalized in the ring? And so this brings us to a couple more examples. One example is this. This is called phenol. Phenol is an alcohol, you know, it's just got the COH. Alcohols, are they very good acids? Alcohols, are they good acids? Alcohols are awful acids. Why? Why are alcohols awful acids? For example, methanol. Is it because the bond is too hard to break? No. This bond's broken with, well, the one I had up there earlier is broken. Is that the reason? No. Oxygen-hydrogen bond has to be broken, these acids to react. Is it because this is not polar enough? This is so polar, we call it hydrogen bonding, right? Very polar. And so why is this alcohol not a very good acid? Well, this alcohol is not a very good acid because, you know, what's the driving force in chemical reactions? The driving force in chemical reactions is we want to go from a stronger to weaker. In other words, from unstable to stable. And so here, this is a weak acid going to, well, the product of this, if a base comes and plucks off a proton, we generate the conjugate base. The conjugate base of this is oxide. Is that a stable product? No. It's very unstable, so we lose H+, and this is what we're going to have as a product. And so methoxide is not very reactive because we're going to generate a highly reactive product. And so we're going from weaker to stronger. Well, it's the same thing. You know, when phenol reacts, we're going to go from phenol to phenoxide. What does phenoxide look like? Well, phenoxide looks a lot like this, methoxide. And so when we look at phenoxide, we'd expect phenoxide to be a strong base. But it turns out that phenoxide is an unusually weak base. It should be strong because when you look at it, we got a negative charge localized on this oxygen and an electron pushing group, right? An electron pushing group here. We got a negative charge on the oxygen electron pushing group here, hydrocarbon group. But this is an unusual group because this is what we call an aromatic group. And aromatic groups have a delocalized pi bonding network. Well, how can that impact this? Well, it turns out that some of that negative charge density can be distributed into the ring itself. And with phenoxide, it's a lot easier to see how the negative charge density can be distributed in the ring. And the way whereas over here, can some of this negative charge density be distributed into the methyl group? No, this is already very electron rich. Do you think it wants more electrons? No. Well, this looks the same, you know, hydrocarbon, hydrogen carbon. It doesn't want electron density, does it? And this is already -1, -1, -1. That's a lot of negative charge density over there already, right? Or does it? And so what happens with phenoxide is these aren't equivalent in terms of energy, but we can draw resonance forms for this and distribute charge into the ring by looking at it in this way. And so what we would see happening is this. For example, lone pair goes into the bond here. Well, can carbon have 5 bonds? Is that possible? Carbon cannot have 5 bonds. And so that would normally prevent it from happening. But what can happen is these pi electrons can pop out of the bond and then become a lone pair on this carbon. And so the structure we end up drawing is like this. So now double bond to this oxygen, 2 lone pairs. This carbon is going to have a lone pair bond to the hydrogen, and it's going to be bonded to another carbon. Like this. This carbon now is going to have the negative formal charge. Yeah. Well, what's better, to have a negative formal charge on carbon or to have a negative formal charge on oxygen? To have a negative formal charge on oxygen. And so this is more stable. This is going to be the dominant form. But, you know, carbon's 2,5, oxygen's 3,5, so it could happen like this. This could be a minor contributor. But if we think of this as a minor contributor, there are more contributors here. my thing. So for example, if this lone pair is pulled into this bond and pushes these lone pair out, we'll end up with this structure here, where we put the lone pair on that carbon position here, and then we make this a double bond here. It converts it from an sp2 to an sp3. You see that? So this carbon goes from it being sp2 to sp3, so it's going to distort the structure. But this is what we end up with. Now the negative charge is on this carbon. And repeat this. Drop these into the bond here, throw these out onto that carbon there. And then if we drop these into the bond here, we'll kick these out back onto oxygen, and we're left with a similar, with a more similar to that. Uh-huh.
Did you say that oxygen prefers only the carbon?
Yeah.
So that would be the more stable?
Yeah, that would be the more stable. These aren't equivalent in energy. You know, this would be the most stable resonance form. You know, but we could have inequivalent resonance forms, right? Then the hybrid would be a biased structure. It's a more stable. And so, in other words, you can see that the charge density can be delocalized in the ring structure. And so, for something like benzoate, benzoate can delocalize some of the charge density into the ring structure, and therefore stabilize the benzoate ion. And so it turns out that benzoate is unusually weak, and phenol is unusually strong. Normally we don't think of alcohols as neutralizing bases, do you? Like if you want to neutralize some base, you could use some ethanol. Would that? No. Ethanol is way too weak. But phenol, on the other hand, I think it's even stronger than acetic acid, you know, which is very unusual for an alcohol to be stronger than something like acetic acid. And so there's no problem. We can neutralize bases using phenol. And so this is unusually strong. Is it unusually strong because it has a weak bond? No. Is it unusually strong because it's unusually polar? No. It's unusually strong because its product is unusually weak. That is, this is unusual. We can draw a lot of resonance forms for this. Actually, technically, probably more because the bond ends up here, so there's more resonance forms we can draw for this. And the more resonance forms you can draw, the more delocalized that electron density is, and the more stable. Okay, so phenol is an unusually strong acid. It's not a strong acid, it's just, you know, we just don't expect alcohols to be very acidic. And benzoate is unusually weak. Oh, this is not benzoate, sorry, this is phenoxide. And so the same thing, benzoic acid, that's an unusually strong acid, right? And look at the polarity. That means benzoate must be stable. There's one more factor influencing the stability. You know, you did your Spartan calculations in a vacuum, right? That means there are no other molecules interacting with it. But if you have other molecules interacting, then it could help stabilize it as well. So for example, DNA, DNA has a helical structure, but if you turn off the hydrogen bonds, you could do this in Spartan. You can build DNA and then turn off the hydrogen bonds and watch the DNA fall apart. Because what's holding it together? It's the hydrogen bonds, right? The hydrogen bonds is stabilizing the helical structure for DNA. Well, the same thing, we could stabilize ions by intermolecular forces. Whenever we make bonds, like hydrogen bonds, stabilizes things. In order to break it, it destabilizes things. And so making bonds stabilizes, breaking bonds destabilizes. They don't have to be bonds, they could be IMFs, because IMFs are just weaker electrical interactions than bonds. And so the final thing we look at is this. We look at hydration, solvation interaction. Hydration and solvation interaction. And this is, how ions are stabilized in solvents. How ions are stabilized. In solvents. Just to give a general example of this, like something like sodium chloride, if you think about bond energies, actually, sodium chloride is a pretty strong bond. Actually, it's not just one bond, there are a lattice of bonds in sodium chloride. And so when we look at the energy, it requires to break a mole's worth of ions apart. We have to break a lot of bonds, actually more than a mole's worth of bonds. Each sodium ion is bonded to 6 chlorides. Each chloride is bonded to 6 sodiums as direct neighbors. And then we have more electrical interactions. The bond energy is 760, around there, in the high 700s kilojoules per mole. This is a pretty strong bond energy. If you go back, and do you remember in chapter 10 what the biggest bond energy you saw was in the chart? The highest bond energy in chapter 10 was close to 1,000, 900 and something, in the high 900s. Do you recall what it's for? It's for N2. The nitrogen-nitrogen triple bond was about 1,000 kilojoules per mole to break, making nitrogen highly unreactive. Highly unreactive because it just takes a lot of energy to break that bond, 1,000 kilojoules. And so this brings up the point, why is sodium chloride with a bond energy, we don't call it bond energy for ionic compounds, we call it lattice energy. And we'll talk about lattice energies in chapter 12. Why is sodium chloride with almost 800 kilojoules per mole of bond energy, why does that dissolve in water? Because when it dissolves in water, it's a strong electrolyte and all those bonds are broken. And so how can water break all those bonds in sodium chloride? It just doesn't make sense because the nitrogen in this room is considered almost inert. Very few things will react with nitrogen. And therefore, nitrogen's known as a pseudo-inert gas, like neon, helium, etc. Non-reactive. And part of the answer lies in the stabilization of the ions. due to solvation or hydration effects. And so that's what we're going to talk about next. But we don't have any more time for today.